if you step in this road during rush hour, you have a 60 or 70% chance of just getting taken out by a car. Everybody is going to step back on the curb and say, oh, I don't want that. But if I say, hey, if you eat a standard American diet, you have this really high chance of getting chronic health problems later in life. A lot of people are like, you know what? That seems like later. How do we get solutions to perhaps the wickedest problem of all, of maintaining population level human health?
Raised this crucial paradox here. Public health is omnipresent yet invisible, much like in engineering. I'm thinking of my ancestors in the Indus Valley, River Valley civilization. They built the Metal Age metropolis, Mohenjo-daro, along with cities like Harappa. And the work that happened there remains as the origins of sanitation. What happened back then, 4,000 years ago, you can see it in modern Manhattan. You can see that centuries later in the Roman system. So you can see these are insights transferred over generations, cultures. This is how society chose to prioritize what's important for people from the get-go. So the fact that it is now invisible, inaudible, and disinvested even now is so perplexing.
Today on Saving Sapiens, we have the incredible honor of speaking with Dr. Guru Madhavan. Dr. Madhavan is a biomedical engineer and a senior policy advisor at the National Academies of Sciences, Engineering, and Medicine. He is also the Norman R. Augustine Senior Scholar and Senior Director of Programs at the U.S. National Academy of Engineering. He has a fascinating background that bridges the gap between cutting-edge engineering and broad societal impact, having worked in the medical device industry, developing cardiac, surgical catheters, and neuromuscular stimulators, and leading analysis on topics like vaccine prioritization, prescription drug pricing, and cancer control strategies. He's a prolific author. I have loved following his writing for some time now, and we are particularly excited today to dive into his work, and especially his latest written work, Wicked Problems: How to Engineer a Better World. Welcome to the podcast. So excited to have you here.
Matt, finally a delight to connect on this platform here. And I'm absolutely confident, much like your listeners, viewers, I will have much to learn from you.
I'm so excited to learn from you. So Dr. Madhavan has a really unique perspective that I'm so excited to host here. A lot of times on the podcast, we have members from the biology community, from the biotech community, from the medical community. And traditionally, a lot of our training is very, very, very focused and very sort of narrow. And there's a really unique and rare feature set with Dr. Madhavan that specifically crosses over between systems thinking, engineering, and biology. And that perspective has been something that I have gained so much from listening to you speak, from talking with you one-on-one, and from reading your work. Break down this dichotomy that so few of us have ever had to think about between the simple problems that we think of when we think of engineering solutions and the kind of complicated systemic problems that you dive into that you call wicked problems.
In fact, let's track back into my own career development, why I even got interested in engineering, because that is beginning to make sense to me years later as I try to engage with the kinds of problem sets that you have just articulated. I studied instrumentation and control systems engineering. And why did I become an engineer? Because growing up in India, everyone around me was becoming an engineer. So I too did it much like an arranged marriage. Everyone was doing it, but it's only years later I fell in love with the profession. And the fundamental doctrine, if I were to say, the fundamental worldview that was presented to me as a systems engineer is control. Efficiency was the destination. Work as hard as you can through your technologies, sensors, transducers, and systems to get there. And so the entire orientation was to this goal. We worshipped goal, a declared destination. Now, that was my undergraduate training, and I'm glad that I had that training largely in the Newtonian arena. But my graduate studies in the United States, and I was selected for a PhD program in biomedical engineering, and coupled with some industry experience and management studies and a fluke elective that I just happened to take under evolutionist David Sloan Wilson, completely transformed the way I think. And I like to say that that particular course uniquely transformed me from a Newtonian into a Darwinian, even though I'm not a formal biologist by training. In fact, after 10th grade, I didn't really study any biology. I struggled through, um, you know, electrophysiology, cell biology, and whatnot in the graduate school courses that are required as part of the biomedical engineering curriculum. And I was even failing in one of the critical courses. And the TA essentially gave up on me, said that just memorize this book. And it was a book by Bruce Alberts and others, the famous book Cell. But it was the math part on the second half of the course that really lifted me up, thanks to a gap junction characterization and how do you plot action potentials and whatnot. So that's something that I deeply enjoyed. But of course, that created a pulse of its own, deepened my interest. I went into cardiac electrophysiology, and then that led me into a brief career in the medical device industry in the Bay Area, where I was looking at surgical catheters. We were trying to treat atrial fibrillation through minimally invasive procedures that got enabled by robotic procedures. And that led me into a second line of work in the medical device world about thinking about kind of a more systemic issue. How do you boost circulation? So people don't realize they have two hearts, of course, the one in the chest, but the equal and opposite mechanism from your legs, the soleus muscle, that's responsible for about 80% return of blood back to the heart. And so I started looking at those kinds of issues, really literally an inverted way, much like how I inverted myself from a Newtonian into a Darwinian to understand the world. But they have synergies. The world we live in really cannot live without both, as though, how we have shaped it for us. There's a lot of incentives in the Newtonian mode than the Darwinian mode. And the Newtonian mode is sometimes instantaneous, it gets you quick gains, quick profits. Darwinian modes, they take their own time. They're not responding to any particular market, so to speak, in this case, Mother Nature. And what exactly are you, quote unquote, designing and for what purpose? So a lot of open-ended questions. So marrying these worlds allowed me to, shall we say, have a split personality, going back and forth as an engineer, deeply captivated by the concepts of complexity. But ultimately, it makes you a responsible professional. How you begin to realize the deficits of the standard reductionist approaches and how you take on more holistic dimensions. But that's not to say that whatever Mother Nature does as positive, pure, puritanical benefits, so to speak. It has to be carefully managed. Not everything Mother Nature does yields positive results. So those are the kinds of understandings I was able to get over a period of time, maybe over a decade, before I started putting all of those things to practice here in Washington through my work at the National Academy.
Now, you're exposed through your work at the National Academies to some of society's biggest problems. You have been vocal about pointing out solutions that we can look for in scenarios that have essentially caused society's greatest minds to scratch their heads. When we're facing massive social upheaval, whether it's from a pandemic, chronic disease, whether it's from things like infrastructure burden where the technology is outpacing the infrastructure to carry the new power demands with oncoming technologies like AI, you have addressed a lot of the things that I think most of us both take for granted, and you've gone head on to correct a lot of the things that are just direct misconceptions. Relatively recently, you wrote a piece that made quite a splash on how we conceive of things like efficiency, how aggressively we should trim things like redundancy in systems in a perceived effort to maximize and optimize the output of a system while minimizing the cost to run that system. Tell us a little bit about why these kinds of wicked problems require us to reconsider our assumptions about easy, fast solutions.
So there are several layers to your question. So let me start with the National Academies, which has been my intellectual home for the past now going 15, 16 years. I was selected for an economic policy fellowship somewhat randomly, and that had a profound impact on how I think about the world. So here I was really doing models related to complexity and understanding what kinds of products can be developed by a more nuanced understanding of the circulatory system, and how do you engage the reflex arcs and activate the nervous system to achieve positive outcomes and in people with various complications. Now, taking that from a deeply individualized approach, maybe a more customized treatment or a support system for a particular individual, to dealing with macroeconomic issues when people didn't quite understand what exactly was happening. Why were certain systems collapsing right in front of our eyes, from mortgage to interest rates, and how adjustments at the top level, let's say through the Federal Reserve, has deep impacts on how individuals alter their spending behavior. These were enormously interesting issues for me back then as I was getting exposed to these kinds of issues. So the National Academies were created by President Lincoln, the heart of the Civil War. The thought was, and I would say it was one of those acts of genius foresights that can be recognized only 150, 60 years later. The fact that the government thought of the need, of the value of an independent organization to provide them advice on any matters of science, engineering, and health. And in fact, the earliest problems that they had were very specific, directed, and had direct impact on economy and national security. For example, this was a time when wooden ships were being transitioned into iron ships. And as soon as you change the technology platform, you get a whole suite of complications that you didn't envision before. Rusting, and thinking about non-magnetic means of navigation, because of course, magnets and iron interact, and you then have a range of issues such as misfiring guns and lost ships and all sorts of interesting complications. So the National Academies were involved in providing technical advice on those matters. In fact, the earliest work that eventually led a couple of decades later for the creation of the gyroscope, non-magnetic means of navigation, all came from the National Academies. So here you have a group of technical experts dealing with the kinds of problems. What we can now call a straightforward material science problem was at one point lacking all the technological insights, could have appeared as wicked problems. Let's get to that concept now, which is the subject of my recent book. So wicked problems, the caption was coined by two scholars, Horst Riddle and Melvin Weber. This was in 1973. I believe it was a public policy symposium at UC Berkeley, and they argued that wicked problems contained no definitive formulation. Each problem is unique, so there's no clear start and stop signs. And each problem is usually a symptom of another problem. So you have no clear entry and exit points. So the so-called solutions aren't really true or false, but good or bad. So it's a matter of value judgments there. And what ultimately remains are opportunities to learn by trial and error. And this is where the evolutionary approach makes enormous sense here. So now it sounds intimidating if you look at the concept of wicked problems. And so that got me really interested in now, how do you engage with them? You don't really solve wicked problems. We often run around saying that we can solve wicked problems. That took me into the topology or even the philosophy of problem formulation, which is often ignored in engineering education and even in practice, because you get rewarded for solving problems. In fact, that is my defining professional identity as an engineer. That's what I was indoctrinated into. I am a problem solver, and there's some pride attached to it. Now, if you look at the various aspects of a wicked problem, you have hard problems, which are bounded. They are boundable, and they are easily shaped by scientific principles, market pressures, sponsor requirements, you name it. They all are neatly specified. Such solutions, in this case, literally solutions, you can solve a hard problem, material mastery, mathematical manipulation, whatever. You can solve them by recombining, repurposing existing tools and techniques. But an extension of those and maybe a deepening of those creates a second class of problems called the soft problems, which are in the arena of human behavior. And they are complicated because of the political and psychological factors beyond just the mathematical formula that we are talking about. And the interesting dimension in soft problems is their endpoints are unclear. And there are a lot of thorny constraints that complicate the problem set. And you can't really solve a soft problem like a hard problem. You can only resolve them. So manufacturing a car is a hard problem, but managing city traffic is a soft problem, which is actually a harder problem. So a lot of different issues. If you just go into the arena thinking that, oh, okay, we are just going to use congestion pricing to solve the problem of traffic, then you have a range of issues coming up. What are people willing to pay? And how is it going to affect differentially the people who are using that service when the demand for that service is at its highest? In fact, the term for this in economics is discriminatory pricing based on the time of the day. So soft problems involve technology, psychology, and sociology here. The third class is a messy problem, which emerges from divisions, differences from our value sets, belief systems. And I think ideas from cultural evolution and behavioral sciences are helping us get better at these kinds of issues. Thought about messy problems, and my technical work at the National Academies through, vaccine development portfolio and drug pricing portfolio have all been around this. So let's imagine a disease outbreak. Okay, you can instantly imagine hard solutions like barcode track supplies or antibiotic deliveries and so forth. We can map it. We have optimized the max out of those things, and we know how to get things to someone when there's need. But then there are soft problems in that outbreak, which is like, how do you map the spread of the infection? And we learned that real time during the COVID crisis. And after the fact, we started thinking about retooling the indoor environment to prevent the propagation of infection. Remember the times when we opened the schools and hospitals and you're sending vulnerable people, kids, elderly people into those locations, senior living homes, and how are you going to retool the indoor environment? Cost a whole range of issues. But in this case, neither solution or resolution is exact as with hard and soft problems, but they're only good enough. So a messy problem has to deal with problems such as like even delicate cultural rituals. We saw that during the Ebola crisis, the burial rituals that had a major role in spreading of the pathogen. And you couldn't just go into a community, just parachute in and say, don't do it, because these are cultural rituals that have evolved over centuries. And people started doing secret burials and others, which accelerated the spread. I think the hard and the soft and the messy really conspire to produce wickedness. And that kind of reinforces my earlier point, because you can't just solve wicked problems. And if you say that you're solving wicked problems, then you're just dealing with an aspect of the problem, which is the hard part of the problem. So let me delve a little bit deeper into a messier dimension that is not often considered in the engineering landscape. And let me go back to the Ebola example, because it is fascinating. It contains hard dimensions we were talking about. Again, to repeat, we had barcode track supplies, the hospital instruments and antibiotic deliveries and whatnot. And then you had soft resolutions in terms of really mapping the vector across different regions of Africa in this case, and how the vector had differential impacts in the equatorial regions than the other parts. But the real fascinating part of it is the cultural element of it. That's something, that understanding, that engagement with that problem, I attribute that to my lessons from David Sloan Wilson here. So the burial rituals were key. And again, as I mentioned earlier, were a critical part of the propagation of the pathogen here. And the standard technocratic health policy approach was to just parachute in and say, do not touch the diseased. Whereas there are elaborate practices around it. People touched, bathed, kissed, and ultimately worshipped their dead relatives on their next journey. And even within that, the Christians had a different pattern than the Muslims, and the pastors and the imams played a major role in guiding those departure ceremonies and whatnot. And as I mentioned, distrusting kind of the technocratic approaches, a lot of people started doing secret burials and whatnot, and that only amplified the problem. The interesting thing, and this happened around the time when I was working on a vaccines related project at the National Academies, and My work intersected with the Ebola crisis and shortly after the Zika crisis, completely different behavioral facets there, which the latter one including reproductive choices among young women and so forth. So with Ebola, I've learned that how do you create, and again, this is where the engineering thinking comes in. How do you create a respectable proxy, an effective substitute for the process of touching, kissing, and bathing the deceased? That's where the anthropological insights were profound. And again, goes back to the work that David Wilson and colleagues have done, and that directly affected the work that I was doing, which led me to explore several other questions, which I'll get to. So the idea was to use a banana tree trunk as the equivalent of a dead body. So basically transfer all the properties of a human being into the banana tree trunk and basically divert all the practices that you would do on a dead human body onto the banana tree trunk. This was stunning. And the community adoption was almost instantaneous because you have transferred the properties from one basic instantiation to the other. And we live in an age of such high tech gadgets, gizmos and whatnot. And here you have a banana tree trunk effectively transferring or adding a different type of significance to that departure ceremony while having public health benefits. And now, how do you think about such technological platforms even for public health prevention preparedness measures? Now, why did we wait so long with vaccines for Ebola? And again, goes back to the economic dimensions we touched on with the problems here. There were multiple front page reportings on how vaccine candidates for Ebola were available, but were shelved because they didn't fulfill the cost benefit criterion of a corporation or the government investing in it. Now, this again goes back to the critique of the Newtonian thinking, cost over health benefits, in this case, quality adjusted life years or disability adjusted life years, results in a fairly confined, compacted, crushed ratio that misses out on several significant parameters that can and do affect public health, and in this case, even vaccine development and delivery, and ultimately public acceptance of public health interventions. So you bring in, let's say, do what in systems engineering we call multi-criteria analysis. You bring in several other dimensions into the surface of analysis and see how the system changes. And if you bring in a parameter such as public dread, which Ebola evokes severely, and also the associated psychology and the interest in just getting rid of the pathogen entirely, so completely treating it. So you bring in those couple other dimensions along with just the standard economic metric of cost benefit, then you will see that something that has been neglected as Ebola or even Zika really shoots up in the rank compared to even standard conditions like flu that we deal with. So there's a lot of money to be made with the flu vaccine annually, just updating them, but not much when it comes to these distant diseases, as people often refer to. So there's a lot of interesting dimensions here. You have the technology aspect of this. You got the economic psychology part of it. You got the social psychology part of it. And ultimately the sheer cultural anthropology part of it that can and does influence how we think about technology. Again, it just doesn't have to be an advanced mRNA platform. It could also be a banana tree trunk that's simultaneously deployed to achieve a public health benefit.
You know, the fascinating constant array of these kinds of comparisons that we encounter in the way that we run public health makes it such a forced sort of apples and oranges comparison. In our sort of easy, everything fits in its unique portion of the box conception of engineering, I think we can assign a team to a specific problem with specific parameters, with a specific budget to fix a need in society. We say, here is your budget. You can fix the bridges. You can fix the roads. You can upgrade the electrical system. When it comes to health spending and engineering social solutions to health problems at the population level, it's not only eye-opening to think about the examples that you bring up, where instead of a multi-billion-dollar drug, sometimes the best intervention is a shift in a social convention or a shift in a particular cultural tradition. We faced instances like this dramatically in the last pandemic to rock the world, when we saw that sometimes the really severe spreading points for COVID-19 were often associated with either mass gatherings of cultural significance like sports or religious gatherings, or where there would be varying acceptances in different cultural subpopulations of the attempted restricted movements and restricted social gatherings. It kind of brings to mind for me the hardest part of the decisions that we have coming up in healthcare. I feel like are often characterized by these sort of wicked dilemmas, if you will, of what is the best use of resources. As a systems engineer, and especially as somebody at the National Academies who is always thinking about these things at almost at a national policy level by default, how do we approach, I'll give you my favorite dilemma right now. How do we approach a systems problem where we have a front end solution and a back end solution? As in, when we can decide how to spend the next $1 billion, how do we compare an intervention that would cost us $1 billion and make, say, the next generation of young Americans really, really less likely to get chronic diseases, but it's almost impossible to measure how an intervention now will impact them 30 years from now, versus spending $1 billion, for example, making improved replacement heart valves for elderly patients who are in the last few years of their life. How do we even begin to compare the variables across such different options?
So there's a powerful concept in the practice of systems engineers. We call it levels of abstraction. And it is almost paradoxical. To get to a very specific functional acceptable outcome, you really have to move far away from the problem. So you have to ascend to multiple levels away from it and look at how that problem behaves at several different levels that we may not have thought of in the close proximity to the problem. For example, take a car. Now you had a collection of cars, let's say 100 of them is a parking lot. A car on its own is a single unit, but then multitudes of them becomes a parking lot. And then you make it thousands of cars. So we are going logarithmically here. So from 1 to 100 to, let's say, 1,000, you have traffic. And then you have 10,000 cars, for example. Then you have the manifestation of 10,000 cars in kind of our day-to-day experience as a suburb. And then you have a million cars. That's a mega city. Then you have 1 billion cars. It's climate change. So how these problem sets manifest themselves, that is, for example, investing in a heart valve, for example, how does it look at multiple, in this case, logarithmic levels, is something that we don't do often. And this is a particular practice of systems engineering, which I think for your listeners, it's important to share. It's a convening mindset more than a controlling mindset. How do we bring in several aspects of the problem, including those that don't even seem relevant to that? And that requires traveling distance, as we just talked about mentally. Systems engineers often try to embrace contradictions when, let's say, a specialist engineer runs far away from it. And I think this is where the evolutionary perspective of engaging with the problem on their terms is profoundly important. Whatever technology that you just talked about a moment ago. The way systems engineers also go about surrounding their understanding about a problem is by developing what we call in trade jargon ConOps, a concept of operations. You can think about them as narratives about a situation we haven't necessarily experienced. So how do you go about that? But in a more practical sense, ConOps are primarily about three things: how a system would work, what functions it could fulfill, and what outcomes it should achieve. And so this would, could, should really gets into some of the questions that you were talking about at multiple levels, because we are expected to take accountable approaches to sane, serious, substantive investments of public dollars, whatever. And how do you advise the federal government or anyone who's involved in that kind of investment to make prudent investments here? For me, over the years, to engage with these kinds of problems that I have gone about, and I discuss them in the book as well, and they make sense both technologically and evolutionarily. So there are 6 concepts that I try to filter my problems through. And in the book, I've detailed them, and each concept, for each concept, I discuss the hard, soft, messy, and their wicked manifestations and how they become. Efficiency is the starting point for that. So we talked about cost benefit analysis and how we, it was decided that Ebola vaccines weren't cost effective, so we shelved them. But that was the final kind of the point. Too often, efficiency becomes the destination, not the starting point. So what if you invert it and again make efficiency as a starting point? So that's how I begin the book. So you start with efficiency, not end with it, and then you bring in other attributes such as vagueness, the sheer ambiguities and uncertainties associated with a problem set. You bring in vulnerability, not just do brute force risk management or risk analysis, that kind of work. And then you think of safety, which everyone desires. And I think it's part of the engineering responsibility to do that. Maintenance, something that we don't openly talk about, openly even recognize in our world, that is captivated by innovation, novelty, newness, and whatnot. So this is the kind of the boring, humdrum type of work, much like what human bodies do, much like what sleep does to human body. Every morning we get up, it's just a miracle. I mean, it's amazing. It's an ordinary miracle that staves off extraordinary menaces, just the act of sleeping and regrouping your systems. And finally, resilience. That's a term that has become too many things in modern thinking. And if you look at even how resilience originated as a technical concept, if you go back to the origins of carpentry in shipbuilding. So that's people decided the bendability, the bending, breaking characteristics of different types of wood and what was best suited for a ship. Much like, you can see the standard technology assessment part of it, which technological platform is good for Zika or Ebola and so forth. So I've taken on these 6 concepts to kind of construct a concept of operations for any problem set that people want to engage with. And as I said, they make sense in multiple dimensions, including evolutionary aspects of it. There isn't a hierarchy among these attributes. Each will produce a relationship and a revelation to the problem. So that's the kind of approach that I have been putting into some of the complex problems that have been given to me at work. So that's how I've been trying to think of a systems approach to wicked problems.
Now, when you go into the way that society reacts to the less exciting components of addressing wicked problems, you talk pretty extensively about what maintenance looks like at a societal level impact. You detail things like what a waste management system entails in a city at scale with a large North American bustling urban center. And it reminded me of a kind of constant battle that we have in medicine to convince the public as best as we can that it is worth putting in health maintenance effort over the length of their lifespan, rather than the kinds of classical interventions that we think of when we picture a doctor going to work, or in a dramatic television scene where a surgeon is saving somebody's life from some kind of life-ending trauma or motor vehicle collision, or some sort of last minute novel drug therapeutic that can end a life-threatening cellular disorder. A lot of health is a wicked problem. And a lot of the steps that you mentioned in how you assess wicked problems in engineering systems is so closely paralleled to the kinds of wicked problems that we see in medicine. And I'm wondering if there's a way that you in the engineering world have come to address the lack of public excitement and interest in the less exciting, less flashy, less news headline grabbing aspects like maintenance, and what we can take away in the medical world from how engineers are addressing this.
I think maintenance makes enormous sense when viewed through the lens of failure analysis, which is bread and butter of most engineering domains. I worked in a very conservative, meaning you don't have too many tolerances, and you just can't goof off too often, especially in the medical device industry. You moved an analyzer 3 inches, you have to get it recertified and so forth. So all of those elements, it's the same idea in aviation, maybe in nuclear reactors and whatnot. So extremely ultra risky systems. I think maintenance, when it comes to supporting or renewing, repairing machines, has blatant outcomes. And if a system is not maintained, the effects are pretty visible. And oftentimes it's life or death, a kind of situation. But you can see in public health, I mean, we talked about the banana tree trunk part of this, right? I mean, it is hardly sexy and there's no market for it. And we still don't talk about it as an intervention. Maybe it's thought of as a local fix that helped alleviate something and people moved on, that kind of thing. And I think that's what whenever I talk about maintenance, I mention this, that we need to be focusing on the vexy, not the sexy, because that most of the human processes are on the vexy part rather than that allows us to do the sexy part, basically. But as we know, human bodies aren't machines. So idea of maintenance that are applied to mechanical systems aren't directly transferable to biological systems. However, we keep doing that. It goes back to this fundamental fallacy that we commit. And as you know, I mean, our good friend and mentor, Randy Nesse, has taught us on this about the body as a machine metaphor has pernicious consequences. And of course, maintenance has a major role in that, but so does several other elements like design defects, like other trade-offs and corrupted plans, and if there are variations in how things are assembled and so forth. But I think a lot of human performance makes the greatest sense through the lens of maintenance. I think you have thought about this subject, and I, of course, welcome your views on if Mother Nature is actually chasing novelty for the sake of it, or is it looking at exploring newer capabilities by maintaining current performance standards or whatever. So the language might not be exactly fitting here, but I think the concept is worth exploring or expanding in this case.
Well, it's in medicine, the challenge is, like you mentioned, that a lot of people still perceive maintenance and the parameters of maintenance in health as though the human body were a machine. And the difficulty in conveying that to a patient population surrounded by things that were engineered with the possibility of maintenance with part replacement is that when people start to think of the human body like a car, if they forget to maintain their car in a certain way and they need a replacement part, whether it's a small part or whether it's an engine block, there's always the fallback that if you're willing to spend it later, your mechanic can still go and put in some replacement parts to catch you up on that maintenance, and your car will be okay because engineered systems are engineered to allow actual standardized replacement parts to give you that sort of catch-up maintenance. And when we try to convey the importance of health maintenance, if anything, the fact that the body is this sort of assemblage of adaptations means that if you don't have health maintenance on a regular basis for a long enough time, if there is ever any of these sort of catastrophic biological failures, like the kinds where we see in chronic health conditions where people become insulin insensitive, or when there's like end stage renal disease, these kinds of things become much, much harder to reverse because we don't have parts that were made for easily standardized part replacement at a later time, because we're contingent living organisms with a specific developmental path. And that's really hard to convey to people in a society where they're used to being able to pay for things as a service to get a replacement part whenever something breaks. There isn't an Apple store with an engineer on the other side who's able to just swap things out for us. And I think a lot of the appreciation that I have for your writing is that you convey a sense of like an artistic walk through the history in order to deliver this brutal fact of how things work on the ground. And man, if that could be conveyed to more people in medicine, we would have the ability to step back from a system that isn't working very well and say, if this isn't working well, what is this system-wide change that we need to make? How do you go about addressing something that is as massive of a system as healthcare in the United States, when you can clearly tell that we're failing at so many of the wicked problems, solutions? How do you even begin course correcting when we're failing this badly?
No, you're getting to the core of the social tension here, right? I mean, there's a concept called future discounting, I mean, which present costs outweigh future benefits. And therefore, we are lethargic and our choices lead to deferred maintenance, which is a pathology that affects society at large. In engineering, maintenance is very specific, it's critical, and is even legally mandated, which in some cases isn't directly applicable to human health maintenance, basically, unless you're required by law to go see your doctor 3 times a year or 4 times a year, whatever. I mean, that's one absurd analogy there. But, infrastructure like railways, bridges, power plants, they all demand very rigorous, regimented inspections. Again, aircrafts, and of course, we have had a lot of accidents and mishaps lately in the aviation industry. And again, whenever such calamities happen, the subject of maintenance becomes crucial. But it's not publicly discussed. It's just one of those hidden discussions. That's why engineering in major companies have gotten really good at developing the predictive analytics software to anticipate failures. Big aerospace companies do that all the time. Again, nuclear reactors, they have to manage material degradation. You just can't afford to be loose on those. And the regulatory requirements change, safety standards change. And then some of these maintenance regimes outlast the creators of those systems in a way. So that's something that is fundamentally different than, let's say, a standard biological maintenance mechanism. With the biology and health, shall we say, the opportunities for maintenance are fairly limitless within the constraint of, let's say, the age span here. For example, I mean, lizards regenerate their tails and organ systems renew themselves while we are asleep. The power of the unconscious here on a daily basis, the astounding regenerative capabilities that we have. How do we think about investing in longevity is kind of the question that connects with the future discounting concept here. I don't think we have a good discussion about this. There's much to be talked about here and thought about here. And I think we're limited in our framing of these problems. And I think you put it very well here. We think of maintenance only when a system deteriorates to the point of damage or reaches a critical point of failure. Those are pretty costly situations. When a machine breaks down, or if you skip a routine service, my car just very proactively gives me the message, maintenance due. So I don't know, how do we think about it as a parallel with human systems? But I think engineering has benefited profoundly from the insights of biological evolution. In fact, we talked about the predictive maintenance using analytics and self-healing materials. I think we have incorporated those in many of our products here. But are we really thinking about a programmed response to potential failures, expected failures, even in mechanical systems, rather than these unanticipated properties that have been shaped by evolutionary pressures here? That's a question I think one can explore in great depths.
It seems to also be a little bit related to perception. You mention in your book that if the maintenance of, say, the sanitation removal services in a large urban center, if they stopped running for a week or two, it would instantly be visible and very stinky, and everybody would be complaining because of the large heaps of garbage bags on the side of the road everywhere. The fact that the problem in situations like that can't hide forces a scenario where the maintenance has to be maintained, has to be paid for, and nobody is ever able to escape very far from that maintenance. With health, we have this sort of odd dichotomy between catastrophic failures at the end of life, where we perform all kinds of medical interventions are very obvious, and we work really hard and we spend a lot of money to save patients in those scenarios. If you're 75 years old and you have a heart attack, we have a very, very well-studied series of interventions, a very well-studied series of sort of diagnostic and evaluative steps. And we are very well prepared in North American healthcare to take care of a 75-year-old having a myocardial infarction. But no matter how much we invest in that, even if we know that a significant portion of 75-year-olds having a heart attack could have had their incidence significantly reduced by a lifetime of proper health maintenance, we cannot seem to muster whatever the either motivation, memory, or fear, whatever the motivator is, to actually invest in and follow through on the health maintenance that would have prevented that. And it's this odd, perhaps a default in this short-term vision of humanity. If I tell you, hey, if you step in this road during rush hour, you have like a 60 or 70% chance of just getting taken out by a car. Everybody is going to step back on the curb and say, oh, I don't want that. But if I say, hey, if you eat a standard American diet, you have this really high chance of getting chronic health problems later in life. A lot of people are like, you know what? That seems like later. Why do I care? And they don't make the same kind of self-preserving decisions. How do we get a system where the motivators are short-term, if they're effective, and convert it into solutions to perhaps the wickedest problem of all, of maintaining population-level human health? If we can't change the hardwired decision-making way that our brains perform these kinds of estimated calculations, is there a way out? Is there something I can do as a provider? Is there something we should all be doing? Or does this have to be a bottom-up solution or a top-down solution?
Raised this crucial paradox here. Maintenance, and by application public health, is omnipresent yet invisible, much like in engineering. So let's take two interesting historical concepts here. The first one goes really back. I'm thinking of my ancestors in the Indus Valley, River Valley civilization. They built the Metal Age metropolis, Mohenjo-daro, along with cities like Harappa that are in present day Pakistan. And the work that happened there remains as the origins of sanitation. Of course, there were attempts prior in other civilizations, but this was kind of the practical civilizational design that they looked at. And the first thing that they focused on was sanitation. And how many reports after reports have been published that sanitation is the single most important engineering support system that has enabled life, not just preserved life. And some of the decisions that they took, which is like, how do you place sedimentation traps? How do you create running water? And literally, how do you separate clean water from poop? I mean, it sounds crass, but I think that's what it took to really supply what's needed for the civilization. Even standardized grid layout of how do you design cities and everything, what happened back then 4,000 years ago, you can see it in modern Manhattan. And some of the original sewer designs, the way they tapered the tubes and how they created collection spots and everything, you can see that centuries later in the Roman system. If you go to Rome, you see Cloaca Maxima, which is still a running sewer system, and it's amazing. There are versions of that in how the Japanese clean their rivers and so forth. So you can see these are insights transferred over generations, cultures, and so forth. So if maintenance engineering was the first choice we made as society, and in this case, I mean, this is far before we were scientists, politicians, musicians, even professional musicians. So this is how society chose to prioritize what's important for people from the get-go. So the fact that it is now invisible, inaudible, and disinvested even now is a perplexing question here. Now, add to this the recognition of maintenance in religious practices, theology even. There's a Hebrew concept called tikkun olam, which is the conscious repair, conscious communal repair of society. And so it is embedded not just in the origins of society, but also in the various religious frameworks that guide society. That's why your point is even more pertinent and powerful here. Why do we continue to not pay attention to this powerful domain of human affairs? I guess we just have to keep writing about it and look deeper, look farther back into history and articulate. I think we just need more people talking about this publicly. I think that's the best we can do.
I'm excited to see what kinds of solutions that we can come up with the more we have these kinds of cross-disciplinary and interdisciplinary conversations where our engineering is informed by evolutionary biology, where our medicine is informed by our engineering and vice versa. Thank you so much for coming on and discussing this with us. To all of the listeners, if you have a chance to pick up a copy of Wicked Problems, it is a fascinating read. It doesn't read like, if you're imagining a sort of dry engineering textbook, it doesn't read like that at all. You do a dramatic and really fascinating fly through of the life of Ed Link that you have worked into this narrative. And if you can take a moment to just kind of give us the cliff notes on why this massive societal branching multidisciplinary issue of solving wicked problems. Why and how were you able to integrate the life of Ed Link? Give us kind of an overview of why this fascinating character became like this braided story throughout the book, and why this, to me, this is such a quality narrative hook that kind of and keeps it exciting and relatable at the same time. Tell us a little bit about Ed Link.
I'm very grateful that you recognize that. And many of the readers of Wicked Problems resonated deeply with Ed Link's story because he's unknown. And so my publisher is planning on a spin-off of Wicked Problems. It's going to be released as it's just purely Ed Link's story excerpted from Wicked Problems. It's called The Blue Box, Ed Link and the Birth of Modern Aviation. It'll be released in 2026. So I talked about 6 concepts through which we can filter a problem through to gain a more nuanced understanding of its nature. So that led me to a parallel. Where else do you have 6 different forces playing at once to keep a system in function? And took me to aviation. An aircraft operates with 6 degrees of freedom. You have 3 rotational axes and you have 3 translational axes. So the chapter titles for Ed Link's story automatically wrote themselves. You have pitch, roll, yaw, surge, sway, heave. When I started the Ed Link portion of the book, which are interwoven throughout the book, I didn't know quite the difference between roll and yaw. In a prior life, I was a crazy man. I did skydiving and so forth, but never got interested in aviation and the technologies per se. So this was also to challenge myself. I wanted to take on something I knew nothing about, aviation, as part of this project, and teach myself how to fly on a simulator. But of course, that led me to dig deeper into the origins of flight training, which is a fascinating history. The book is dedicated to, and it is based in the city of Binghamton in upstate New York, where Ed Link, who didn't even pass high school, created a profound piece of systems engineering that enabled modern culture and how it connects, collaborates, whatnot. And again, goes back to kind of the politics of recognition we were talking about minutes ago, Matt, why we disregard maintenance or why we don't discuss maintenance enough in public affairs. Much like it often talk about, there's an analog here. We celebrate flight and Wright brothers, and duly so. And they basically gave us wings in a way. But flight training is what led to the kind of the systematic practice of flight. And one could argue that flight training, thanks to Ed Link's work, is as important as flight itself. So Wright brothers, and again, I'll go through all the details. And at one time, flying was just too expensive, and it was costly in terms of life and limb. And how do you prepare for the war, and how do you prepare for space missions, ultimately the moon mission, and all the other cultural connectivity that came from transcontinental transport here. So what the Wright brothers did as part of their demonstration is, again, duly recognized. But the work that Ed Link did is hardly discussed. So it was my attempt to bring to the fore some of the real work that goes in making something happen. If the Wright brothers demonstrated flight, over a series of experiments, I think the first attempt, it took about 59 seconds or something like that. But that those attempts didn't require systems engineering. What EdLink did required this kind of the careful fusion of technology, sociology, and public policy that gave this. So his invention was called the blue box, literally. So the pilot sits inside the box, and it is only through the darkness, lacking a reference to the horizon, you learn about the various parameters that one needs to confront when learning how to fly. This was called the blind flight. And what EdLink did was instrumentalize that helped create a standardized approach for a lot of people to train, especially during World War II. The Allied forces quickly trained using Link Trainer, and the rest is history. So the notion of flight and the notion of flight training gives us a good substrate to think about how do you deal with the pulls and the tugs and dealing with the disorders and the disturbances that one encounters aloft. So that turned out to be a useful metaphor for me to build off of to engage with wicked problems. So that's the parallel. So book became a hybrid of sort, kind of dual tracking these things, and it took twice as long as it did. It took about 6.5 years to compose the whole manuscript. But I'm really glad that Norton is coming out with an EdLink edition of the book called The Blue.
And all of your readers out there, you will see the effort put in, because it really truly finds ways to illustrate really deep, really complex problems and the attempts to come up with solutions to these problems, and manages to weave this narrative arc through as well. And weaving this narrative arc through is a captivating walkthrough of a part of American history that we all think we know, that we most certainly do not have a very, very accurate take on. And for those of you in the audience who might be setting out mid-career anywhere along in a STEM field, if you feel like you need inspiration for how the efforts of one person can have nearly inconceivable extent and very, very, very significant magnitude, EdLink's story is a real inspiration to see kind of the broad world-changing impacts that the efforts of a determined individual can bring.
Often we treat public policy choices, even public health choices, as a blind taste test. You see, you have to pick one over the other and see. I mean, we started talking about vaccines and how do you prioritize them and whatnot. But in reality, they are a blind flight test. You have to deal with these onslaughts of parameters and in motion, and you have serious stakes, and lives depend on any decision that you make. So that's why EdLink's work becomes even a kind of a meta framing for the kinds of thinking we ought to be doing.
Thank you so much for joining us today, everyone out there. Go grab wicked problems.
Thank you, Matt.